Hello, everybody. Good morning. Welcome to today's session, which is going to be on the lunar eclipse. So next Sunday, not at 11 o'clock morning like today, but 11 o'clock evening, right? Midnight, you're going to have a very interesting phenomena that I would like all of you to observe. And it's going to be one really long lunar eclipse. So today we are going to discuss a bit about the lunar eclipse. I'm going to just explain a few concepts related to the lunar eclipse. Okay. So today, of course, is 31st August. So we are talking about 1 week away, Sunday, midnight. So from 11 o'clock, okay, from 11 o'clock, midnight, not nearly, just almost midnight. It is going to be 82 minutes long. It's going to be a long lunar eclipse. So what we are going to do today is that we are going to take up different points about the lunar eclipse. So I'm going to explain some of these. I have a small presentation that I will show, but I will also be discussing certain key ideas that you probably need for this. Okay. Karthik here is with me. So Karthik, as they ask doubts, you can share those with me. Okay?
Sure, sir. Yeah.
I can discuss that. So hello, everybody. Hi. So let us get started. So I'm going to go step by step. And if there are any doubts, please do ask me. Okay. So first, let us start with why are we even discussing about lunar eclipse, right? So basically, the longest duration of total lunar eclipse that is possible, theoretically possible, nobody has observed this, is 107 minutes. It's extremely rare. It's going to happen when basically the moon passes right in the middle of the Earth's shadow. And it's going to basically be at the farthest point and so on. So happens very, very rarely because everything has to coincide. So the theoretical longest duration is 107 minutes. But very close to that, okay, on 16th July 2000, there was a lunar eclipse that was observed for 106 minutes, 25 seconds. If you think about it, it's very close to 107 minutes, right? 106 minutes, 25 seconds. This was, in the last 100 years, the longest lunar eclipse observed. There was one earlier than that was observed, which was 106 minutes, 35 seconds, I think. Okay, or 32 seconds or something. The next longest lunar eclipse that you can observe, which is for 106 minutes, 35 seconds, but none of us will be able to observe it because it is going to happen on 19th August. Not this year, not next year, not the year after. It's going to happen 19th August, 4,753. 4,753. Obviously, nobody's going to be alive, right? So you're talking about like a few thousand years away. That is when you're going to get the next longest lunar eclipse. Lunar eclipse is quite a rare event, right? There is one coming up next Sunday. So Sunday midnight, 7th September 2025, you're going to get an 82 minute long lunar eclipse. That's quite long. If you think about it, 82 minutes is quite a long lunar eclipse. So kindly don't miss it. Okay, because after that, you will not know when you will get a chance to see a good lunar eclipse. So 82 minutes is quite a long lunar eclipse, more than an hour. It is going to start at 11 p.m. India time. 11 p.m. India time on 7th, nearly midnight, little bit before midnight, right? 1 hour before midnight. And it will end 22 minutes after midnight. 22 minutes after midnight. Okay. By the way, so we will be talking about, remind me, Karthik, to talk about, if we have time. I have not put that as part of the main presentation. Okay, Karthik, just remind me. If we have time, we will talk about Umbra and penumbra.
Okay.
Umbra will be the deep shadow of the Earth. So when we talk about Umbra and penumbra, you will see that there will be this lightening or like less brightness of the moon that will happen when it passes through the penumbra region, and you will get a much darker moon, basically like a proper full eclipse when it passes through the Umbra. That is also the time the moon will turn red. Okay. So, and of course, yes, We should hope that there are no clouds. Okay, so let us hope that so that we can see it properly. But this is 82 minutes long. Okay, enough of this. Let me now get started with why do we get lunar eclipse. So before we start, I just want to highlight what are we going to cover today. We are going to learn about what is lunar eclipse. So first we are going to focus on that. Then we will look at the question, why don't we get lunar eclipse every month? First of all, why do we get lunar eclipse? Then if you understand why we get lunar eclipse, the first question that will come up is, why can't we get this every month? And then we will try to figure out the difference between phases of the moon, which of course you get every month, and lunar eclipse, which you don't get every month. And finally, we will try and understand why is the moon red in color during a lunar eclipse. By the way, that is related to why the sky is blue. Okay, and so we will discuss some of these. But let us first start by looking at what exactly is a lunar eclipse. Okay, so this is the sun. So assume that this is the sun. The sun sends us light. Of course, it sends it out in all directions like that. And the moon is here. So how do we actually see the moon? This light from the sun hits the moon, and then the moon reflects it. And some people on the earth will see it, right? This is the night time. For these people here, it will be the night time. So for these people, it is night. And so they can see the moon like this, right? Because the light from the sun is hitting the moon and coming there. But what happens is when the moon moves this way, then the light that comes from the sun, which should have reached the moon, is sometimes getting blocked by the earth. So it actually never reaches the moon. So the moon basically, right, does not reflect the light back to the earth. And so if you're standing here, in principle, you should not be able to see the moon, right? Because this light has not reached the moon. So this is the reason why you get an eclipse. Basically, if you see that the sun, the earth, the moon, they form an almost straight line, right? The moon can go all the way till here, from here. So there is this region. There is this region where you will have lunar eclipse. So basically you can say lunar eclipse happens when the sun, earth and the moon are aligned in a nearly straight line, not perfect straight line, right? Because you can see that the moon can have different positions, slightly varying positions. So as long as the moon is here, there, you will see that the sunlight is actually getting blocked. The sunlight is getting blocked by the earth. So that means no light reaches the moon, and therefore the moon is obviously not able to reflect it. So this is the basic idea of a lunar eclipse. Now the question that comes up is, if you look at the moon keeps going around, no, like this. So let me show you here. Oh, so another way. This is one way to think about it. The same thing you can also say that forget the moon. Generally, the sun's light should keep going in all directions. So the earth is blocking this part of the sun's light. So that means behind the earth, there must be a shadow. There is a shadow. So you can say that the sun, actually sun's light is blocked by the earth. So this is the shadow region. Now the question you can ask is, wait a minute, shouldn't the shadow region keep growing bigger? No, because the sun is not a point object. And this is where we will later learn about Umbra and penumbra. I'm not going to focus on that, Umbra and penumbra, and we are only interested in the Umbra region. Okay, this is called the Umbra region. So this is very dark shadow, right? So no light from the sun reaches this part. So if the moon is here, obviously the sun's light will hit the moon, and part of it will like from this region, right? So suppose sun's light comes and hits the moon here. From this region, right? This region is bright. So this region, you can actually see the light. Now you can say, but these people are like seeing the sunlight, so it will not be dark enough. I mean, the light, moon is not going to be bright enough. But what if you're standing here? That also will receive some part of the light. So you can see the moon, right? You can see the moon here. But when the moon goes around like this, if it goes into the shadow region, like that, right? Once it enters the shadow region, that means no light from the sun is going to the moon. So moon is obviously not able to reflect the light back to the earth. So this is the region where you have lunar eclipse. And how long will it last? Like I told you that the upcoming one next week is going to be 82 minutes, right? Next Sunday. So you can see that as long as it's moving in the shadow, so it's moving from here all the way till there, right? So that time, that will be total lunar eclipse. That will be total lunar eclipse. Now, obviously, the first question that comes up is, but the moon goes around the earth once every month, right? It will go around like that once every month. Okay, I've not drawn it very well, but let's say that it goes around once every month. So next month when it does this, again it should have a lunar eclipse. Then 1 month later, again it should have lunar eclipse. But you know that lunar eclipse doesn't happen every month, correct? So the question then is, why don't we get lunar eclipse every month? If it's just that Earth, Sun and the Moon have to be in a straight line, they are going to be in a straight line once every month, right? Isn't it correct? So why don't we get lunar eclipse every month? So every time the moon goes behind like this, you should be getting a lunar eclipse. That should happen once every month. So why is it not happening once every month? Okay. Now I would like all of you to quickly answer in the chat box. Why is it that you don't get lunar eclipse once every month? Come on, quick, tell me. Everyone tell me. Let's see it. Makes sense, no? If it keeps going back around like that, every month there should be one lunar eclipse. Why? Why doesn't it occur every month? Does it occur once every year? Technically, it can occur twice a year, but it doesn't occur. Doesn't occur because there are a lot of things that have to happen. But first of all, why doesn't it occur once every month? Think about it. No, it is not because of the Earth's axis. No. Why is the moon not in the shadow region? Just imagine, no? If this is the shadow region and every month the moon is going around, it has to go through the shadow region, isn't it? No. It turns out that there is a very interesting reason for this. The orbit of the moon is tilted. Okay, let us try and understand this. The orbit of the moon is tilted. Let me show you. So let's move on to this. So here you can see the moon's orbit is tilted by 5 degrees to the Earth-Sun plane. If you look at the Earth and the Sun, if you think of the Sun-Earth, the Earth is going around the Sun like an orbit. So you think of the orbital plane, the moon is not in the same orbital plane, the moon is tilted. Now, when it's tilted, you have to understand, it is not tilted. Sometimes people think that when it's tilted like this, when it goes here, the tilt will change. No, the tilt remains the same. It is not tilted like this and then tilt is changing this way. No, it is not tilted that way. It is always going to remain in the same tilt. You can see that here. This is the plane. So what if there is a tilt by 5 degrees? I'm going to show you with an animation why this makes a massive difference. Okay, so let us see this. Why the tilt makes such a big difference. I'll come back to this diagram. So notice. So I want you to look at this. So this is the moon. This is the moon. The sun is far away. Somewhere here, the sun is far away there. Okay, so I've not shown you the sun. So you can see that the sun's light is coming. This is the moon shadow, which is not important, just to point out where the moon is. This is the earth and this is the earth shadow. You can see that there is this dark region of earth shadow, Umbra, and there is this lighter region of earth shadow that's called the penumbra. Okay, why is that there? We will talk about that if we have time later. But notice, as the moon goes around, wait a minute. Every month the moon will make one trip, right? So once it comes here, won't it basically become an eclipse? Watch what happens. Watch what happens. I'm going to show you here. Okay, watch the moon. It's taking a month, right? In 1 month's time, the moon is coming closer, 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 closer. Ah, it looks like it's an eclipse. But no, it is not an eclipse. Why am I saying it's not an eclipse? Because we are observing this in 2-dimensional plane, but you have to actually observe it in 3-dimensional plane. This orbit is looking like this, but you have to see it at like properly. Like if you see it 3-dimensionally. Okay, so sorry, let me go back. Let me go back. I made a mistake. Sorry, let me just continue. I made a mistake here. I should have. I should not have pressed the screen. Just hold a second. Okay, just watch. It's going to be very interesting. So, yeah, so you can see the moon is doing this, right? You can see the moon doing this. So it's entering the shadow region now. It's going to enter the shadow region. But you have to now watch this in 3D. So I'm going to tilt this. I'm going to tilt this. Okay, so watch as I'm tilting this. 1 second. Okay, let us continue with this animation. See this. Now, do you see that in 3 dimensions, though it looks like it was in the shadow region, it is not really in the shadow. The shadow is going a little bit above. So sun's light from here, sun's light, right? The sun is somewhere there. So this is the sun rays. So sun's light can reach this part, and it does. Sun's light reaches this and bounces off back to the earth. So will you be able to see the moon? Of course you'll be able to see the moon. Not only will you be able to see the moon, you will be able to see full moon. Full moon. It is not an eclipse. It is a full moon here. Okay, let me clear this up. So I want you to understand this. Okay, I'll show you this again once more. So you can see that that is the tilt. So that because of the tilt, right, the moon is actually moving around like that on a tilt. After many months, once in a while, the moon is really coming into the shadow properly. Okay, let me show this again. Most of the times, the moon is not in the shadow. It looks like, if you see it this way in 2 dimensions, it looks like it is in the shadow. But because the moon's orbit is tilted, it is actually below. It is below. The shadow is there. You can see that the shadow from the sun to the earth is there, and the moon is below. So that means sunlight will reach the moon. And I'm showing this over several months. So several months, the moon is always below the shadow, right? And then suddenly you'll see, now there is this one time where it is actually right in the middle of the shadow. That is not going to happen every month. That will happen once in a while. If the moon happens to be here at that time, then yes, you will get a lunar eclipse. So I hope this is clear. So Karthik, can you quickly do a poll? I want to make sure that everybody's understood this before proceeding. Did you understand this? Okay. So basically the moon is going, like if you think about the earth, sun there, let us say that the shadow is here, the moon is going like this. So only when the moon reaches the plane of the earth-sun plane, right? But that is going to happen only when it happens there. So that is one point. It is not like this. The moon is not going around like this, because then that will basically be in the same plane. So therefore, every month you should be getting a eclipse. No, that won't happen. Okay, because it's this way. There is one point here. If the sun was here, earth was there, moon is there, then it is possible. But that's a rare event. Okay. The orbit changes very rarely. You're not talking about the orbit change at all. I'm talking about the moon. The moon's orbit, this is the earth. Think of this as the earth. The moon's orbit is tilted. If you think of this as the earth-sun plane, this is the earth, that is the sun, earth-sun plane, moon's orbit is tilted. Let me try to explain that with another diagram. So let's see this. Okay. So let's see this. So if you see this, okay, you see that the tilt is not changing. Note, tilt does not change. It remains the same tilt throughout the year. There will be a small change that will happen over several years, but that we are not interested in. This tilt is almost the same throughout the whole year, right? It is not like this portion, the tilt is away from the sun. There also it should be this way. No, the tilt doesn't change. The tilt remains fixed in space. So it's the same tilt. So you can see that if you look at the moon's orbit, this is the tilt of the moon's orbit. When does the moon's orbit hit the earth-sun plane? At this location and this location, right? Now, obviously, the sun is here. So these 2 points, when the moon is there, it's obviously not in a straight line. So the only place when you can get an eclipse will be this point. Possible eclipse places. Possible eclipse, lunar eclipse places. Right? If the moon happens to be here, but notice the moon can be here, the moon can be here, there are so many options. When the earth is at this location, which happens once every year, no? This happens once a year. This happens once a year. That means these locations, the Earth is going to take 1 year to make this trip. So once in a year, the Earth is here. Once in a year, the Earth is there. At that time, the moon could be in any of these locations. If it was here, if the moon is here, when Earth is here, which by the way is a very big coincidence, no? Then only you will see lunar eclipse. Same way, when the Earth is here, if the moon was here, then you will see lunar eclipse. But the moon could have been there, could have been there, could have been there, so many options. So even when the Earth is here, often you don't see lunar eclipse because the moon has to get to that point. So, in fact, the fact that we even see it, because there are so many, it doesn't have to be exactly in the line. It can be in so many locations. So sometimes you will get partial moon eclipse and so on, lunar eclipse. So you will get that. But basically you have to understand that this is a rare event. Does not even happen usually once every year. Okay. So when the moon is here, sun's light, actually this part gets bright, right? Because this will receive light. But you can't see it because you're standing there. You're on the Earth. So that means you will see a new moon. But this is not eclipse. It's not getting blocked. When the moon is here, okay, I'll show you that. When the moon is here, so the moon goes there. But because of the tilt, what will happen is that the sunlight will reach the moon. So this part of the moon is bright. And it will reflect it back to the Earth. So we will see full moon. Okay. So you need this Earth to be behind the, the moon to be behind the Earth. If you take the sun, Earth as a line, moon to be behind the Earth, but it should also be in this line, in this plane. In this plane means this point or the one behind. This point, right? The Earth has to be here or there. So only in these two places you can actually get eclipse, lunar eclipse. When the Earth is here, you won't get lunar eclipse. Earth is here, you won't get lunar eclipse. No lunar eclipse, no lunar eclipse. So only 2 times in a year you can potentially get lunar eclipse. 2, the moon has to be just behind the Earth at that time. You see that a lot of stuff has to happen, coincide for you to get lunar eclipse. Okay. So what is the difference between phases of the moon and lunar eclipse? Let's try and understand that. Okay. So we're going to focus on this. So first, understand the difference between phases of the moon, okay, and lunar eclipse. Just I'll show you visually what is phases of the moon. Okay. So obviously, you know, you've seen this very often, like new moon. Then you have a crescent moon. Usually when you have a crescent moon, you can see a small outline. You can see a small outline. Okay. Then you can see first quarter moon, waxing gibbous, it's called. Okay. Full moon, waning gibbous. Waning gibbous basically means it's like 3/4. 3/4 of the moon. But it is basically now this is reducing. This is increasing. It's going to become full moon. That's why it's called waxing. And this is called waning. Waning means it's reducing. Then you get the third quarter. And then you get a waning crescent. So this is the waxing crescent. And after the waning crescent, it will go back to the new moon, right? So you know this. But let me now show you with a nice animation the phases of the moon. So you can see crescent moon. You can see the gibbous moon, full moon, right? So as the moon is going around, you see one half of the moon is always bright. But when you see it from the Earth, that is when you get this. One half of the moon is always illuminated by the sun, except during lunar eclipse. Okay, that happens rarely, right? Whereas what you see from the Earth is only a portion of the brightened face of the moon. Okay, so let us now try and understand this with a small experiment. So I just want to show you this. Okay, let's go back. So this lady is holding this ball, which she's going to call as the moon. So her face, think of it as the person standing on the Earth, and this light is obviously the sun. Okay, so she is going to take this and move around. So this is a nice simple experiment to do. And what she sees, she will also show you separately. I'll show that. So right now, notice, okay, so before this happened, notice that this half is always illuminated by the sun, except during lunar eclipse. So this is half. But she's not going to see this because she's seeing the backside. So what is she seeing? So she's seeing this. And if you ignore that little tiny portion, this is actually like a new moon. So she's seeing, we are now showing you what she's seeing. Can you see that she's actually seeing new moon? New moon basically means no moon. Think of it that way. So this is the new moon. Why? Though one half of it is illuminated, she's seeing the back side of the, we never actually see the back side, but she's seeing the darker side of the moon. Now you can see that there is a nice crescent moon. Half of this is illuminated. Half of the moon is illuminated, except we can't see the parts that have been illuminated. We are only seeing this portion, which is the crescent moon. Okay, that is the part that we are able to see. Okay, and you can also see, let me go back. You can also see here. Okay, so you can see that always one half is illuminated. One half is illuminated. Let me just go over this. So notice that, can you see that here you can see one half is illuminated? But here you can see that the part that she's seeing, which is the one from the earth, that is dark. So this is new moon. This is new moon. And as she keeps turning this now, notice that you can start seeing a crescent here, crescent moon. But notice that this is still one half illuminated here. What we see is the faces. But actually the moon is illuminated half. Half of the moon is always illuminated in all of these cases, except during lunar eclipse. That's the big difference. Lunar eclipse, that half which should have been illuminated is not illuminated anymore. During phase of the moon, what we see is changing. But the moon surface, half of it is always illuminated by the sun. Okay, this is the gibbous moon. And there's a very nice animation, which also I'll show you after this. You can see here it is full moon. Notice that full moon you see when the moon is behind the earth, right? If you say the sun, earth, moon is behind the earth, but little bit above or little bit below, depending on the tilt of the axis, right? It is not exactly behind, it is above or below. So that's when you get the full moon. And if she continues like this, you start seeing that this part is a little darker, right? So that means you see the gibbous moon here. And you can see now again a quarter moon, last quarter. And then if it continues further, you'll start seeing a nice, beautiful crescent moon. Can you see that's crescent moon? And so on, right? So that's the basic idea. So that clearly tells you what's the difference between the phases of the moon and the lunar eclipse. Okay. So I'm now going to look at a nice simulation. So let us look at this simulation. So let me take you to that simulation first. Let me pause this and share my screen. Just hold on. So you can see this simulation I'm going to show you. So as I move the moon around, watch here. This is going to tell you the crescent, right? Like right now you can see this is full moon, new moon. Okay. And as I move this, notice that half of it is illuminated. Half of it is illuminated. Can you see this crescent here? Because this person is looking at only this portion. When you see this person can only see that little tiny portion. Now that tiny portion will look like this crescent. As we keep moving, can you see that? So crescent moon, I can keep going around. So at this position, you see waxing gibbous. Now, it's not lunar eclipse, not lunar eclipse. This thing is tilted. It's tilted axis. So you have to think of the moon as being above there. And so sunlight reaches the moon and then reaches this person. So you can see full moon. Over a month, you can see the moon is new moon to I'm just taking this around and you can see new moon to full moon. Right? So anyway, so we can stop here with this. Let us move back to just a second. Let me stop this. Okay, so let's move to the next one. Okay, guys, I think you should be focusing a bit on what we are discussing rather than wasting your time on other discussions. Anyway, that's up to you. So let us move on. So let's go to why is the moon red in color during a lunar eclipse? Now, this is very, very interesting. Okay, this is related to why the sky is blue. This is related to why the sky is blue. So I want you to think about this carefully. So first of all, think about how the sky should be if you are in space. If you are not looking at the sky from the earth. What is the sky? You look around and you know that the sky looks blue. Okay, so why is the sky blue is a very nice question to answer. Anyway, let's go ahead and look at the moon. So you see that as the moon enters the Umbra region, it becomes red in color, red. So you will see this on 7th. By the way, this is something you should not miss. Okay, this is something you should not miss. On 7th night, midnight, okay, go up and look at the sky. Hopefully there are no clouds. And then you will be able to see the moon turning red. By the way, a lot of ancient people used to think that the moon turning red, like blood red, it is becoming like blood color and so on. They thought it was an evil omen. They thought that something bad is going to happen. But there's a very nice and simple explanation. It is related to the fact that the sky around us during the day is blue in color. Okay, let us try and understand this. Let me explain this. So from the animation, I'm probably going to move a little bit to understanding. So I'm going to probably write it. Okay, so I want to just show you how the moon is basically becoming red. You can see that. Okay, let's move to the next one. This was a photograph taken on 31st January 2018 when they could see the lunar eclipse in Thailand. Okay, so in Thailand, they took this photograph. You can see moon is nice and red. Okay, nice red color. Why is the moon red in color? Not because of water droplets, nothing. Even from space, moon will look red in color. Why will moon look red in color? That's what we're going to see. And that is related to the fact that the sky is blue. Sky is blue. Let us understand this. And I'm going to need a little bit of explanation that I need to do for this. Just give me a minute. Let me switch over to a writing screen so that I can explain. So let me share my writing screen. Hold on. Where is this? No. So, non-stop sense. Lunar eclipse means we will not see the moon. So how will we see the color red? Lunar eclipse doesn't mean that you will not see the moon. You will see that it becomes suddenly very dark. Okay. And not only has it become very dark, it has become red. So lunar eclipse, you will actually see the moon, except that you will see it in color red. So why do you see it in color red? That's what I'm going to explain. Okay. That's what I'm going to explain. So give me 1 minute. Give me 1 minute. Let me just share the screen because this will require a little bit of the concept behind it that you need to understand. So let us look at this. Yeah. Okay. So let us say, I'm going to need many pages. So hold on. Okay. So let me see. I hope you can see this, right? Yeah. So basically, let me draw the sun. I'm going to make the sun yellow in color, though it is Technically, we should be thinking of it as white. Okay, so, and I'm going to draw the Earth. I'm going to draw the Earth. And I'm going to draw an atmosphere around the Earth. Okay, I'm going to draw an atmosphere around the Earth. What color shall I choose? Okay, let me pick this color itself, green itself. Okay. Obviously, the atmosphere is not this big the way I've drawn it. I'm going to make it look much bigger than it is, just for us to understand. Okay, just for us to understand. So, first you have to keep in mind that this is the atmosphere, this is the Earth. So, this is the Earth. I'm pretending that this is the atmosphere. So, sunlight is coming out. Now, you know that sunlight is composed of all colors, VIBGYOR or you can call it. This is high frequency, low wavelength. Small wavelength, high energy. Okay. Whereas red, so blue, violet, they're all very high energy light packets. Whereas red, infrared after that, so there's also infrared. There is ultraviolet on that side. All of these are higher and higher energy. All these are lower and lower energy. Low energy, big wavelength, large wavelength. So what does it look like? So if it goes this way, this is the wavelength, very, very small wavelength. This you can think of as being blue. Whereas this is red. Okay, so red has larger wavelength, blue has smaller wavelength. So just understand that part. Now, light, the white light that we get is actually a mixture of all of this. And that white light is going to come in like this. And of course, it's going to hit this region. It's also going to hit that region, right? It's also going to pass this way. Some of it will go like this. Some of it will go this way, right? So this is how, so a person who is standing here, for them, the sun looks like in the horizon. So this is either evening or morning. So for this person, it is evening. Whereas if a person is standing here, they'll say, oh, sun is right at the top. So that means for this person, it is midday, noon. Of course, the sun is going, Earth is going to turn. So, but this is basically the idea, right? Now, what happens is that atmosphere is made up of molecules, air molecules. Now, let us think about, I'll just give you an analogy. Suppose you're walking on a street and you come across something like a small pebble. Do you actually change how you walk? So let us say that you're walking, tack, 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 tack. You'll see this pebble and you'll just simply cross. You don't even care. Did the pebble affect your walking? No. You did not jump. You didn't do anything. Right? So this pebble is too small for your leg size. So obviously nothing is going to happen. On the other hand, suppose you had a boulder, like a bigger rock. Now what will happen? As you are walking, you will see this and you will turn around, you will go around and walk, right? You will either jump over it or you will turn around. So something is happening. Correct? Now suppose I make this even bigger. Suppose I say, okay, I have like this really huge block like this. You can't jump. So what will happen? You will change the direction of your motion. And this is an analogy. Okay, this is, don't take it as absolute. Now there are these molecules. Now when you have this red light which has a big wavelength, this red light which will be having a big wavelength, it will just simply go like this. It will just go across the molecules. So red light just simply passes without no problem, not affected. Okay, by the way, light is not exactly your walking. Okay, let me explain that. Okay, then we'll have to get into what is the wavelength of light, how does it actually interact with matter, all of that. So I'm giving you an analogy for you to understand. So basically, if you look at large wavelengths, so they are large wavelengths, they can just simply go over these tiny molecules. Okay. On the other hand, if you take blue, the wavelength is very small. Blue wavelength is very small. It is almost the same size as this molecule. I'm not even talking about water molecules. Okay. It's also like nitrogen, oxygen. So when it comes like this cannot pass through. So it will get basically scattered in different directions. One time it will do this. The next one will come here and get scattered like that. The next light, blue light, will come here and get scattered. Of course, it will also happen to indigo. It will also happen to violet. It will also happen to green, etc. But more of the light sent from the sun is around yellow. So sun will send yellow, orange, red. So sun sends a lot of yellow, orange, red, green, and blue. It sends less of those. The sun has, okay, we can say the sun is yellow color. Not really, it's white, but broadly you can think of it as peak intensity of radiation is around yellow. Okay, so there is a very interesting thing about how the temperature of the sun is related to the yellow color, but all that is getting into too much physics right now. So a lot of blue light will come, a lot of red light will come, but notice that the blue light is getting bounced off, scattered. So this has a name. It is called Rayleigh scattering. Rayleigh scattering. Okay, so low wavelength, small wavelength, high frequency. So high frequency, small wavelength gets scattered. What color light is that? Blue. So basically, if you look at this, all these areas, blue is getting scattered. Of course, it's getting scattered like that also. Okay. And so from here also it's getting scattered. Now you are standing here, and if you look at this part of the sky, this part, of course, you see the sun. But here you will see that blue light is reaching you. Notice, if light was not getting scattered, then how will the night sky look? Or not even night sky, day sky look? Okay. By the way, that's a very interesting question for you to think about. If this blue light was not reaching your eyes, how will the sky look? Okay, you can't really see light that does not reach your eyes. So let me explain this. So let us say that this is the Earth. Suppose there was no atmosphere, and this is what is going to happen if you are going to watch the sky from the moon. So from the, let's say that this was the moon. Moon or no atmosphere Earth. Okay, suppose the Earth had no atmosphere, then what will happen is the sun is sending out all this light, right? We cannot see this light. Can't see that light. It is not reaching your eyes. So you can only see the light that is reaching your eyes. So suppose you stand here midday, right? So this light you will see. So you will see super bright sun. Bright sun. So you're seeing bright sun. And then in this direction, when you see, you will not be able to see any light because there is no light reaching you this way. So you will see pitch dark. You will see black. During midday, you will see black sky everywhere. Think about it. It's not even easy to imagine this. I want you to just imagine this, right? From the moon, you look at the moon. Think of it like midday of moon. Sun is right there. Floor is all bright. Floor is all bright. Okay, so the moon's surface is bright. Or if there was no atmosphere on the Earth, the same thing will happen. Earth's surface on the ground will be bright. But you look this side, like the sun is there, that will look super bright. You look this way, it is pitch black. Black sky. Now you don't know how it even looks. It is going to be black sky with a bright sun. It is not a bright blue colored sky. I'll show you how it looks. I have a small picture of that. So let me first show you that, and then I'll come back and continue this. Okay. By the way, this is also related to a lot of other things. This is one of my favorite topics to explain, but today, of course, we are not going to have that much time. So let us see. So this is a blue sky, right? But this is how it will look. Pitch dark, pitch black. Okay. Everywhere it will be black sky. And you may, even when you have sunlight, so for example, maybe there was a sun here and you will see bright sunlight here. And if you're standing here and there was no atmosphere, you will see this as being bright, but you will still see this as dark. This will be still black, with some stars here and there. Okay. Why? Because in all direction, you don't get light from any other direction. You're getting light from this point star. You're getting light from that star, this star. But most of the region, you're not getting any light from. So it is going to look like this. So daytime on the moon will look like pitch black sky with a bright sun. Okay. Which, by the way, you can't even imagine properly. We are not used to this. So the moon is going to look very bright on the surface because there's a sun there, right? But you look this direction, it is pitch black with some stars here and there. Okay. So you will not really see something like a sky, correct? When you don't have an atmosphere, you don't see what you call the sky. Okay. You don't see what you call the sky. So you'll see everything as being dark black. Stars here and there, of course, you can see the stars, but you will not be able to see a sky the way we see it on the earth. Let me now go back to this thing. You have to see, you have to spend some time to understand. This is not an easy idea to understand. And so what is going to happen, just coming back here, what is going to happen is because mostly the light that has basically got scattered away by the molecules is all blue, this person, all these people are going to see blue. All these people are going to see blue. Now, what was coming here is blue plus red. All colors, of course, with GR, but mostly you can see things around blue and things around red. VIB, no? Violet, indigo, blue, all of this is with, I'm calling it B. Basically, it's not just that, all of those are getting scattered away. So now think about the person in the evening. So let me redraw this. In the evening, this light that was coming from here, which was white, comes here, right? And it has to go this way to reach your eye. Let's say it's in the evening, you're watching the sun. Now, what is going to happen? I'm going to draw this and show. This is actually blue plus red. I'm just going to call it blue plus red. You understand blue basically means violet, indigo, blue, okay, and red basically means orange, red, yellow, all of that together. But broadly, this will look red, that will look blue. So you say blue plus red is white. Actually, VIBGY are all colors together. But what is going to happen is as the light progresses this way, there's so much of the atmosphere. Notice that it's actually going through less of the atmosphere here. Whereas here it has to go through a lot of the atmosphere. So as it goes through this much atmosphere, the blue is getting scattered out. So this guy is seeing a blue sky. But he's not seeing blue sky from this light. He's seeing blue sky from that light. Okay. The blue part of that light is basically being sent to this fellow in the noon. So the noon fellows, the fellows who have noon right now, they are going to see the sky, but they are not seeing it from their sunlight. They are seeing it from your sunlight. The sunlight is going to reach you, but that part of the sunlight got scattered off to them. So that's what they see as the sky. So now what is going to happen is that the rest of the light is now going to become orangish. Right? Because the blue is gone. Blue is gone. Right? Some more blue will go. So it will become even more orange. So let me call this yellowish. Originally it was yellowish because there was some little bit of yellow. It was orange, yellow, everything. But as more and more blue gets scattered, because these guys will also be seeing the blue, no? Sorry, these guys will also see the blue. What is happening to the light? As it progresses, it is getting more and more. Okay, it's basically the orange is gone. I mean, the blue is gone. So that means it's going to become more and more reddish. Okay, it's going to get reddish and orangish. So in the evening, the light from the sun that reaches you is orange. So that is why, this guy sees blue. This fellow has stolen. Okay, the noon fellow, think of it this way, the noon fellow steals the blue. Not really, the blue was scattered, steals the blue part. Blue from the sunlight. So the evening fellow, this evening fellow only sees the orange part. So why does the sun look orange in the evening? Because a large part of the sunlight, the blue part of it, right, large as it's moving through the atmosphere, blue part of the sunlight got scattered away in different directions. So the rest of the people see blue sky because of this, right? But then what is left over of that sunlight is the non-blue part. And if you remove the blue part away, then that means you're going to be left with more of the red and orange color. So that's why you see orange sun. Okay, this is interesting, right? So it is explaining the blue sky is related to the orange, evening orange colored sun. They're basically the same. By the way, morning also the same principle. Now for this fellow, it is morning. Okay, but then the morning person is going to see the sun like this. But as it comes in this way, a lot of the blue from here will be scattered. And so what is left out will be the orange part. So that's why in the morning and in the evening, the sun looks orange. Daytime, well, when you're here, noon, it starts to look more and more white or yellowish white. Okay. And of course, at night, we don't see it. But the blue sky is related to the orange sun in the evening. Okay. Now, what has this got to do with the red lunar eclipse? So let us understand that next. So let us say that this is the Earth. What am I doing? This is the Earth. I have to draw this. This is the Earth. And I'm going to, of course, draw a nice big atmosphere. Now, light, refracts. Refracts. That means it bends. Okay. So, usually, sun's light should not reach the backside. No, suppose I say that this was the sun. Sun's light should not reach the backside. It goes straight. Goes straight. Okay. But when sunlight goes like this, it bends. It bends. Right? The atmosphere bends this sunlight. Well, it will start bending it continuously because it's not like it's not like one place where it bends. It will bend it throughout. You know that if I had a glass piece, as light enters, right? So it will bend the light towards the normal. So it will bend it like this. And when it comes out, it will again go back this way. So you see that the light has bent, right? Instead of going like this straight, it has got bent like this. And so this bending is called refraction. But that is basically because you have nice refractive material of uniform density, right? Refractive density. But here, that's not the case. You're going to have various densities. So it will bend like this. It will bend like this. You know this. You learned this about mirages and so on. Okay. So you probably learned this already. But sunlight is getting refracted. And so because it's got bent, it is now going to come out like this. Hey. So that means there is light there. But much less intensity. And what happens, as I already told you, this sunlight as it passes out, right? It is basically scattering out the blue. And as it does that, this portion basically becomes more yellowish. And then it continues scattering the blue. Still there is some amount of blue left, right? And then as it becomes more and more of that, it is going to become orangish. Orangish will basically be yellow plus orange plus little bit of blue and red. And it now scatters out even the remaining part. So what comes out turns out to be red. So what is coming out here is red colored light. Okay. And it is bent because of refraction. And the same thing happens to light that passes this way. So all around, sunlight that is passing like this, okay, is going to be bent. is going to be bent. Of course, I have to properly bend it. So let me show you. So it is going to be bent like that. But the way it is going to be bent is because it is scattering out the blue. Okay. So first part of the light will start becoming yellowish in color. Right. And then as you progress, it will become orangish in color. And then finally, by the time it comes out, what is remaining is only the red. And so this is basically red light. Now, during lunar eclipse, this is the only light that reaches the moon. This is the only light that reaches the moon, right? So if I have only this light reaching the moon, let's say somewhere here, the moon is, let's say, somewhere here. Okay, so you notice that what color light does the moon get? It is all getting only red color. So all this is red color. Sorry. All this is red color light. The red color light is sunlight, but it is actually reaching it after refraction through the earth. So obviously, what color do you think the moon will look like? And this is, of course, getting reflected back to the earth. So people here are going to see, hey, what is going on? Moon has become red in color. Yes, moon has become red in color, but that is exactly the reason why, because the earth has stolen out some of the blue color. The earth has taken out the blue color. So we are going to see the moon as red. So I hope this is clear. Karthik, was my explanation clear? Did you understand? Did everybody understand?
Yes, sir. Yeah. I'll also ask in the chat as well.
Yeah, please ask the chat also. Okay, so I hope this is clear. So let us now stop this and continue with what we were doing, discussing. Just a second. Where is that gone? Here. Okay, so you're able to see my screen hopefully now, everybody. Yes, Karthik. So
yes, sir.
It's clear? Yeah, very good. Thanks, Venkat. Yeah. So let us now continue. Let's continue. And basically, this is called Raleigh's effect or Rayleigh effect. So sunlight from here that's coming in. Okay, I'm not going to show it in red color, but yeah, okay. So remember, the atmosphere is very thin. I've made it all thick for you to see. If that was such a thick atmosphere, we would be always seeing red color everywhere around us. But anyway, so this thin atmosphere is good enough for, you can see that the blue light is getting scattered that way, this way, etc. But what is getting bent like this and what reaches the moon is red. So that's why we end up seeing a red moon. So let me know final part. I told you in the beginning, right? In the beginning, some of you probably joined a little later. The theoretically longest duration of lunar eclipse is 107 minutes. Okay, lunar eclipse happens when the moon passes into the Earth's shadow, as I showed you with some of the other diagrams. It has to go into the Earth's shadow and it can stay in the Earth's shadow maximum for 107 minutes. Okay, that happens, a very, very rare event. Okay, the longest lunar eclipse observed in the last 100 years was on 16th July 2000 for about 106 minutes, 25 seconds, very close to the maximum. The next longest lunar eclipse will be on 19th August, 4,753. So you can say close to 2,700 years away, right? Quite a long time away. Now, obviously, none of us are going to be alive for this. So thousands of years away. So that will be 106 minutes, 35 seconds. You can see that scientists now have a very good way to predict a lot of what will happen when you look at the solar system, particularly, and moon and what is happening around us. These things are very easy to predict now. Okay, with computers, we can do like very nice simulations and get accurate answers. So, and that's very deterministic, unlike many other things that will happen. Okay, what will happen to the economy? Hard to predict. What will happen to the human body? Cancer, all these are very, very hard to predict. But eclipses, okay, how will the Mars move? Very, very deterministic, easy for us to predict. And the next lunar eclipse is going to come up in 1 week's time, Sunday. So next Sunday, please stay awake at midnight. Okay, a little bit before midnight, 1 hour before midnight. The total lunar eclipse will start at 11 p.m. Total lunar eclipse will start at 11 p.m. on 7th September. The end time will be 22 minutes past 12. Okay, so it will be 8 September early morning. 8 September early morning. Basically, like you have to go past midnight, 22 minutes past midnight. So it will be totally for 82 minutes. Don't miss it. This is going to be a spectacular show. Very, very important. Now, let me just quickly, let me see how much time I have. 12:03. I should stop. Give me 1 minute. I will probably just explain a little bit about Umbra and penumbra. And with that, I will stop. Okay. So let us just quickly discuss about Umbra and penumbra. I told you that the start time is 11 p.m. That is for total lunar eclipse. Total lunar eclipse. Why do we have something called an Umbra and why do we have something called a penumbra? So let me just show you that by sharing this screen. Hold on. Just a second. All this sharing, changing screen and all takes a little bit of time. So just a minute. So, okay. So I'll explain what is Umbra and penumbra. Okay. So first to understand Umbra and penumbra, you have to understand how shadows are formed. Well, shadow, basically light source is getting blocked. Light source is getting blocked. That's how a shadow is formed, right? So suppose I had a point light source. Suppose the sun was a dot like that. And let us say this was the earth. Okay. Now, light from here will get blocked. This light will get blocked. This light won't get blocked. This light won't get blocked. This light won't get blocked. Right? This light will get blocked. Block. Won't get blocked. Correct? So you can see all this is not getting blocked, but this is getting blocked. Till where will it get blocked? Till the tangent, right? So this is where you will go. This will just pass. Anything inside that will get blocked. This will just pass. Okay. Anything inside that will get blocked. Correct? So if I have a point source, all this region will be shadow. This is shadow. Full darkness. Okay. So suppose I had a point sun. Point light source. Why do I keep saying point? Because you're looking at all this argument is point light source. So point sun. Right? Then you don't have an umbra, penumbra and all. You'll have only full shadow. This is full darkness. And here you'll have full brightness. Correct? All these are fully bright. All these are fully dark. That is not how things work. Because we don't have a point sun. Sun has a size. What happens because of the sun's size? So let us discuss that. So sun, you have to think of the sun as not a point object, but something like this. Earth, let us draw this as the earth. Now, what is very interesting is that if I now look at light, from here I can have this light going that way. Okay. And here also light can go that way. So this place will get light from the entire sun. Okay. But if I now take a point here, the light from here can reach there. But the light from here cannot reach, no, because it's passing through the earth, so it will get blocked. This light that should have reached there is getting blocked. Notice this is getting light from every point on the sun. This is not getting light from these regions. It is getting light from a few of these places. Now, if I draw this line, all these points will get light from the top region. Okay, but look at this. From here, this line, right? I will remove some of these so that you can see it better. I'll remove this. So can you see that anywhere here, suppose I pick up a place, let me pick up a point here. From here I can draw this. From here I can draw this. And the earth is not blocking. Earth is not blocking, right? So that is fine. This region you will get. So let me remove that. So in this region, okay. you get full sunlight. But in this region, if you take this point, no, you will get sunlight from the top part, but you won't get from the bottom part because this will get blocked. See, if I try to get light there, this light I can get. It is passing without hitting the earth. But see this, it is going through the earth, which obviously is not possible. So this is going to be semi-dark. It won't be fully dark, it will be semi-dark. So this is going to be semi-dark. Okay, and I can do the same here. I can do the same here. So just to make things a little easier to understand, I will remove all this. Okay, so you can see that this region, the light from the top can reach, but the light from the bottom can't reach. Now let me do the same here. So everywhere here, light from the top can reach. Here, light from the top can't reach. And if you take this light can reach, right? This light can reach. What about here? Light from the bottom can reach here, but from the top, you can't have the light reaching here. So this is a semi-dark region. This is the fully dark region because no light reaches. So this is called Umbra. And this region is called penumbra. Of course, it won't just be like a thing like this. It will be a full circle. So when you take shadows, you will see a dark shadow and then there will be a little bit around it, which will be a lighter shadow. And by the way, that depends on the size of this. Suppose I draw the sun as a big object and Earth as a smaller object. Then you will see that the Umbra and penumbra regions will be very different looking. This region, no light can reach because if I try to look at anything here, it won't reach. On the other hand, this region, some light can reach. Okay, so this will be fully bright. Fully bright. This will be fully dark. And this will be partially dark. So this is called penumbra. Partial is penumbra. Okay. Penumbra. Fully dark is umbra. So total eclipse will happen when the moon passes through the umbra region. So let me clear this up. Okay. So let us draw the moon. Let's make the moon a small, tiny circle like that. And so if I now take this moon around, as it goes around, here you start seeing the eclipse start, but you will still see some amount of the moon and you can't actually figure it out. Okay. So only when it, because this is bright enough, some part of the sunlight hits the moon itself is bright enough. So only when the moon goes here, now it basically starts becoming quite dark. And so this is the total lunar eclipse. So from here to here, this is going to be 82 minutes. Notice when if the moon was passing somewhere here, then you will see that it is going to take more time. Okay, here is going to take less time and so on. So obviously the time duration of the moon's eclipse will depend on whether it's passing in here or whether it's passing there, where is the shadow, all that. So basically from here to there, this is going to be 82 minutes. That is the calculation. Okay, and you're going to see that on September 7th. Okay, right. So with this, what I'm going to do is to close this part and let's go back. And just a second. Let's see. Yeah, so let's share this. Okay, so I hope you had fun. And so countdown begins. Don't forget to watch the eclipse on 7th September midnight. 1 hour before midnight. It's going to start at 11 p.m. on 7th September. Go on till 22 minutes after midnight. So with this, I'm going to stop. Thank you Okay, I hope you had fun. So all the best, all of you. Okay. Some of you have doubts. I'll just take a couple of doubts. Let's imagine there's an astronaut on the surface of the moon. What color of the lunar surface? So if the astronaut is standing while the sun is shining right on him, by the way, it's going to be very, very hot. The lunar surface is going to be super hot because there's no atmosphere. So sunlight is going to come and hit the surface. But sky is going to look super dark and black. Okay. Except the place where the sun is shining. Ideally, that fellow should not be standing on the surface like that. Of course, with space shoot and all, maybe they will be able to, but it's going to be very, very, very hot at that part of the surface. And of course, you can see the surface because it will be all bright. Surface will be bright as you see it, except there'll be lots of shadows also because it's ups and downs, a lot of craters. Anyway, so I will stop here. I'll stop here. So hopefully all of you have understood everything that I've explained so far. So let us all together watch the moon on September 7th. Okay? Bye. Good night. Not good night. Good day. Good night is on that day. Okay?